So today let's see how to solve shortest path problem, which is also known as Dijkstra's shortest path algorithm or shortest path problem. So for example, if I take, we have a given railway network connecting several cities. Like here we have Mumbai, Pune, Nagpur and Nasik. So it is required to find the shortest route between two cities, Mumbai, Nasik and Nagpur, and these are the weights of a given graph. So I wanted to tell what I want to convey here is, suppose if there is a network of graphs, just like how it's given in the diagram here. Here in the network of graphs, we have few cities like Mumbai, Pune, Nagpur and Nasik, and also a weighted edge. Let's assume those are the distance from Mumbai to Pune, and Mumbai to Nagpur, and Mumbai to Nasik. So if you want to travel the shortest path from Mumbai to Nagpur, you definitely have two options, which is you have one edge with 700, you have one more edge with the 600 and 200. But we don't know which is the shortest path to travel to Nagpur. For that, to solve the shortest path problem from a vertex A or vertex Z, that is nothing but your Dijkstra's algorithm. So let's see here, like we're given an algorithm for solving a shortest path problem. The algorithm was founded by Dijkstra in 1959, is also known as shortest path problem. This algorithm gives the shortest length of a path from vertex A to vertex Z. Just like I said, this gives the length of the vertex from shortest length distance from your source. This can be your source and this can be a destination, anything. Suppose if there is another line from Pune to Nasik, you definitely have, and this is 500 or something. So even if you want to travel from Mumbai to Pune, you definitely need to find shortest path. One is this 650 path or 650 and 500 path. So now let's see how to solve Dijkstra's shortest path algorithm. So here I have an example graph where we will be solving the shortest path from source to destination. So if you observe the graph, my source and destination will be represented in the form of u and v. I will take the source and destination in the form of u and in the form of v, which means u is your source and v is the destination. So if I'm taking 0 as my source, this is my starting point, and if I have to go to the 6, which is my ending point, or which you can tell is the destination. So here you always have to remember, before you begin starting the Dijkstra algorithm, your initial, since there is no any weight for a given graph. If you observe the given graphs from 0 to 1, you have a weight called 2. From 1 to 3, you have a weight called 5. So initial, let's assume that we have 0 as our distance from the point of 0. Okay, so this statement comes to picture like, if your d of u, d is nothing but your distance and c is nothing but the cost. Is d of v. Okay, so what is d of v? How you calculate d of v is, d of v is equal to d of u as c of uv. So let me tell you how this is calculated. So suppose, let's assume 0 as our initial state. So we start with 0. So 0 has two cases to go here, that is 0 has 1 and 0 has 2, which means you can traverse from 0 path. You have two ways to traverse, that is from 1 and that is from 2. So let's consider both the cases. U of v, that is 0 to 1. Okay, using this, if this is your most important formula, using this we're going to calculate much of our problems. So if d of u plus c of u comma v should be, if it is less than v. So if we are starting with 0, if we are starting with 0, if we are taking this starting point as 0, we definitely have to assume that the other vertices are infinity, because we won't know the values of them. So we'll assume, yeah, we'll assume them as infinity. Okay, so here since we have assumed all these as an infinity, if we are starting from 0, like how I said, we have two edges to traverse from 0 to 1. Like I can, from 0 you can take any two paths because it's a starting stage. So using this, dv is equal to du plus c of v, that is a cost. So your 0, if you are traversing 0 to 1, it will be 0 plus 2, which means it is 2 less than infinity. So since 2 is less than infinity, your path in 1's position, or your path in your infinity which is in 1 will become 2, which means 2 has been the shortest distance. So in the same way, let's take from 0 to 2 as well. So if I am taking 0 to 2 as 0 plus 6, because I have a weighted edge over here, 0 plus 6 is equal to 6, which is less than infinity. So your weighted edge, or your weighted graph, your weighted edge from 0 to 2 is 6. So 0 plus 6, 6 is less than infinity. So which means your infinity has a weight, or has a value of 6. So we have found out for 2, and we have found out for 1, and we have found out for 2. So which means we can um, take off this 0, which means we can forget about the 0 and we can start with 1 and 6. So now while starting with next step, that is this all becomes your first step. This becomes your first step. So when your second step starts with recursion of second step in all the cases, like suppose if you compare your, if you compare you have traversed from 0 to 1 and you have got your 1 value as 2, and you have traversed from 0 to 2 and you have traversed and you have got your 1 value as 6. So here if you take the value of 1 and 6, when you sorry, not 1 and 6, the value that is 2 and 6, 2 and 6, your 2 is your shortest number, your 2, the shortest distance among them is 2, which means now you have to start taking from 1. So when you look at 1, you have only one edge from 1 to 3. So you can just traverse from 1 to 3, which means 2 plus 5 is nothing but 7. So here you got your weighted graph as your 7. See, if you traverse, since 1 has, from 1 to 3 you have only one edge, even 1 to 0 you have one more edge, but since this is already met its limitations, we have crossed that one out, which means we are not going to consider this. Only we have to consider the upcoming or the ongoing shortest paths to forward the algorithm. So here from 1 to 3 we have only the another edge from 1 to 3. Therefore it is, you're adding the value which is already in 1 and you're continuing it with adding with the weight of the edge, hence you got 7. So now your 3 value is 7. Okay, so you are done with 1, so we can strike off 1. So now if you compare among, you can just compare among all the infinity among all the vertices, among all the vertices you still have these three infinity vertices which we don't know the value, hence we'll be taking the numbered values. So here 6 and 7. So if you take 6 and 7, your shortest value is your 6. So we'll again proceed with 6. Now 6 has two edges, that is 2 to 3 and 2 to 0. 2 to 0 you cannot take because we have already crossed that out. So the only left edge is your 2 to 3. So when you traverse from 2 to 3, you can simply add 6 plus 8, so which is 14. So here 14 is the number which you get, but among these two, the shortest number is 7, so you will stick with 7. So your infinity is still 7. So let's cross out 2 as you have completed 2. Okay. Now the only digit that is left for you to traverse is 3. Same as 0. So 3, you traverse from 3. Your 3 is 14. It's not, so your 3 is 7, which is not 14. Hence, so you strike the 14 and you continue with 7. So your value of 3 is 7. So the same way, from 3 you cannot go back to 3 to 1 or 3 to 2 because it's already completed and we don't want to take it. So the remaining edges left is 3 to 5 and 3 to 4. So when you continue with 3 to 5, so here 7 is nothing but 22. And from 3 to 4, it is 7 plus 10, which is nothing but your infinity value becomes 17. Okay. So among these, now this will get cancelled. 3 will get cancelled. Okay. And now among 4 and 5, the shortest numbering is your 17. So we'll take from 17. From 17 you have two places to carry on. You cannot go back to 3, or you have 5 and you have 6. So when you calculate from 4 to 5, you have value called as 13. You have a value called 13. Now among 22 and 13, the shortest is 13. Henceforth, you will proceed with 13 as 5 and you will cancel the 5, which means you take the shortest distance. And for 16, it is 19. Okay, so we are done with 14, we are done with 4. So we'll strike off 4. Now you have another numbering, that is 5. So from 5 value, you have 13. So which means both 6 is 19, 19 is also the same. Therefore, your 6 remains with 19. So we have traversed for all the part 5 also. So in this way, or in this manner, this is how you traverse a graph in Dijkstra's algorithm using the shortest path method. That means individually traversing for all the cases in looking from one vertex. So here until now we have been seeing only for undirected graph. So let's see how to solve Dijkstra's algorithm, or the shortest path algorithm, even using the directed graph. Okay. So here I have another example for directed graph where S is my source and E is my destination, and I have other vertices with a direction. Okay, which means it is given with a direction. So for this, the basic criteria or the starting criteria that we did for undirected graph is also the same. But here we're going to find the shortest path from S to E. For example, this is my example criteria which I'll be taking for S to E. So if I start from S, S is 0, while as all my other vertices will be infinity. Okay, so here let me take it in the form of tabular method. So here I'll take S, A, B, any order, in any order, but since S is my source and E is my destination, I'll go in the alphabetical order. A, B, C, D, and E. So S, initial stage, S is 0, and all the other vertices are our infinity, which means we still have to find the value for them, but right now s is our s stands in 0, so the minimum uh, so the minimum value in this column is 0, so yes. Okay, now s, if you see, it has a direction for s to a and s to b, which means it is going from s to a, it's not vice versa, so it's going from s to a. So from s, from 0 to a, we have 0 plus 1, which is 1, and from s to b we have 0 plus 5, which is 5, while other vertices remain infinity itself. Okay, so now the minimum value, if we take the minimum between 1 and 5, is your, the lowest is your 1. So 1 stands for a, so which means here it's 1 and here it's 5. Okay, we are done with this, we'll cross over it. The 1, so 1 is a, so your next traversing path from s is your a. So from 1, that is your a, if you traverse, you cannot go back to s, even though it is not crossed out, the direction matters, which means it is going from s to a and not a to s, so you cannot consider it. So you can see here we have a to b and a to d, as well as a to c. So a to c, which means 2 plus 1 is nothing but 3, and 1 plus 1 is nothing but 2. Since I have not got any other values, I am taking the directed values. And 1 to 3 to 1, we also have 3 here. I mean 2 plus 1 is 3. So here from A to C we have 3. From A to B we have 3. And from A to D we have 2. Here we do not consider 5. We won't be considering 5. We'll cross over 5. We'll take the value as 3 because that's the lowest. Okay. So among these values, 3 to 2, the lowest is your 2 value, so we will go with D. That means our next shortest path that we can proceed will be our D. So D, if you see, D has the shortest path of only D to E, as others cannot be traversed. So the one that is completed is A, so I'll cross over A. Now in D. So when we continue with D, we have only D to E, that is 2 plus 2 is 4, while other paths remain infinity, which means we cannot consider. So here among 5 and 3 we take only 3. So for the shortest path from here to D to E is 4. So it's your E. So in total, if we have to calculate the shortest path from S to E, is nothing but your, this is your shortest path, is A, D, E. Even without traversing other digits or the other vertices, you still have an answer for S, A, D, E. So if I would have considered S to D or S to C, we could have traversed in different directions to proceed, but this is from S, A, D, E, which means the way. So in here, if you see the S, A, D, E part, which means from S to A and A to D and D to E, the S to A is 1 and A to D is 1 and D to E is 2, which means 1 plus 1, 2, 2 plus 2 is 4, which means your total value is also 4. This is how you calculate directed graphs, how you calculate Dijkstra's algorithm using directed graphs and undirected graphs.